conventional method, which you have studied in last semester, has some limitation. So this conventional method of architectural system design, which you have studied so far, has a severe limitation that it does not give any framework for estimating expected performance. After this design, what you should expect from your structure. Okay, that's why this is also called prescriptive design. So there are some prescriptions given in the code, some do's and don'ts. So you follow those good design practices, and there are certain limit states on member forces. So those limit states you have to satisfy. So once you satisfy those, it is deemed that the building will perform satisfactorily during another. But it never defines what is meant by satisfactory performance and how to ensure that the building will satisfy that performance or not. So, to take care of this limitation, we have performance based. Performance based design has some performance objectives. You define what do you want from your building or your structure. So you define what performance you want. And when we want the performance to be defined, it needs two parameters. One parameter is the performance level, and that performance level corresponding to a hazard level. And there can be single performance objective, there can be multiple performance objectives. Okay, so you have to define performance level of the building corresponding to a hazard level. Just to give you an example, it may be that life safety at design basis earthquake, design basis earthquake level. So this is our performance level and this is hazard. So when we say this performance I want from my building, then I need to also tell at which earthquake you want that. Because any building for a smaller earthquake is going to work better, and for a larger earthquake its performance is going to be not that so good. Okay, so when we are defining a performance level, we have to also define the corresponding hazard level. At what hazard you expect that? So we will talk about both of these in more detail. Okay, so this performance level is representing the extent of damage what extent of damage is acceptable. Okay. Extent of damage can be descriptive. You can describe it, that what you expect. But the client will understand the description. Okay, that what do you expect? The infill should not fall, infill should not crack, the beam should not fall down, column should not crack, or if those are cracking, the crack should be limited to an extent that it is not causing any life-threatening injury. So that type of description you can do. But if you have to design, then you can't design based on the description. For that you need some concrete parameters to design. So we need what we call engineering demand parameters, EDP. Now if you have to quantify damage, let us say in a beam, how you will quantify the damage? One way of quantifying is that you can describe the cracks, what type of cracks are occurring, okay? What is the width of those cracks, where those cracks are located, whether those cracks are flexural cracks or shear cracks, so that you can describe, okay? But if you have to define it quantitatively, how you are going to define it? What can be the quantitative parameter?
The width of the crack or the depth of reflection.
Depth of
Deflection.
deflection. Okay, so you have to define the deflection of the member or deformation of the structure or displacement. In displacement also, particularly the post-yield displacement. Up to yield, there is no damage. The damage will start after the member has yielded. Then there is a permanent displacement, permanent deformation. That permanent deformation is measure of damage. Okay. So that's why this method is also called displacement based design, DBD. So performance based design is essentially displacement based design. Okay. Contrary to this, our conventional method we call force based design, because there we are checking the member forces. You have seen in your first semester when we are designing any structure or building using the conventional force based method, we calculate the force demand and we compare that force demand with the capacity or rather limit state, the particular limit state of capacity. Okay, so we compare them. So that is a force based design. But the damage cannot be quantified by the force. Why it cannot be quantified by the force? Because any member cannot take force larger than its yield capacity. Okay, more than its yield capacity, the force it cannot take. So if you apply the force larger than its yield capacity, what is going to happen? It will fail. The displacement will go on increasing, but the force is not going to increase. So you can't define the behavior of the structure post-yield in terms of force. And that's why force is not a good indicator, an EDP, okay, for defining a performance level. It is the displacement, especially the post-yield displacement or the plastic displacement. So our performance-based design will focus on the post-yield displacement, calculation of post-yield displacement. How much post-yield displacement or plastic displacement or inelastic displacement is being caused, or permanent displacement. These are the different names for post-yield displacement. So whatever displacement is again post-yield, that is permanent. If you remove the load, it doesn't come back to the original position. That much displacement remains there. So the plastic displacement, post yield displacement, inelastic displacement, permanent displacement. So that is our main parameter which we have to evaluate. And to evaluate that, we need nonlinear analysis. To consider inelasticity, we need nonlinear analysis. So almost 60%, 60-70% of our time in this course we are going to devote to nonlinear. To understand the nonlinear analysis from the basics and then to implement it in software. Okay. So far you have been exposed to linear behavior of the structures. You know how to calculate the linear displacement of any complex structure. You have done classical methods in your graduation, how to calculate displacement, elastic displacement. Then you have learned finite element method where we also did matrix analysis. Okay, so you know how to calculate the displacement, elastic displacement of a structure. What we have to extend it is how to calculate the displacement post yield. When this linear methodology is not valid, how to calculate that displacement. So number of methods, lot of work has been done on this. So many methods are available. We will, in this course, will have some exposure to that. Then, displacement is one, and this displacement can be represented either in terms of the different engineering demand parameters we are talking about. So the first engineering demand parameter is post yield displacement. Because the damage is best represented by post yield displacement. Post yield displacement can be the post yield curvature of the structure. Curvature can represent the displacement, deformation. Okay. It can be slope or it can be displacement. Okay. And these are related. Curvature is related with slope, slope is related with the displacement. This relationship also we will study. This is also represented in terms of, in case of buildings, inter-story drift. Okay. Inter-story drift is also important for non-structural elements. Okay. Inter-story drift gives us the extent of damage, or it can be used to quantify the damage in our structural components as well as non-structural components. Okay. When you think of non-structural components in a typical building, let us say hospital building, okay, what are the typical non-structural components which come to your mind? Infills. About infills,
Pipeline.
can we call infills non-structural? Are those structural or non-structural? You have studied the role of infills in frames in your.
If there are embedded partitions, we can say that non-structural elements. Embedded partitions don't take any role.
So infills are non-structural in the sense that the safety of the building does not depend. If the infill collapses, the building is not going to collapse. Okay. But these are sharing the force. These are taking the lateral force from the frame. Okay. So whether these are structural or non-structural, it's somewhere in between. It has some aspects as non-structural, some aspect it has as structural, because it can change the force distribution in our structure. So it is different than other non-structural components which are not sharing the lateral. These are sharing the lateral. Okay. But in outer plane action, infills are both in plane and outer plane action. So these can collapse in outer plane action, and outer plane action, it is not resisting any lateral. Okay.
So, inter-story drift and story drifts are different or similar? What this means?
Interest, generally, we write story drift. Okay. Specifically, it means interstory. So correct term is interstory drift. Because here we are making it clear that we are considering the relative displacement of one floor with respect to the floor below. So which is occurring within the story. When you say story drift, conventionally it means interstory drift, but somebody may get confused. He may take the drift, the displacement of the floor with respect to ground. That also he may call or she may call drift. So to clarify that, we use interstory drift. So the term which we are using it is interstory drift or interstory drift ratio, which is very clear that it is delta I minus 1 divided by hi, which is height of that story. Okay. So interstory drift means we are talking about one story. The relative displacement occurring in one story. So infills are one non-structural components. Okay. Then yes.
In a load bearing structure, we will consider infill as
In load bearing structure there are no infills. There are masonry walls. So the masonry walls in load bearing structures will be called load bearing wall. So those are load bearing walls. Infills we call only when we are putting these masonry walls in a frame. Then these will be called infills. So if it is a masonry building, then the walls themselves are the structural elements. There are no columns. So those walls themselves are actually the structural elements. But in case of a frame structure, the frame, RCC or steel frame, that may be structured, and infills may be treated as non-structural. But whether we treat them structural or non-structural, in reality, those are affecting the load distribution in our structure. So that we have to recognize. So even if we declare them non-structural, we can't ignore them while analyzing our structure. We have to consider them. So that's the difference between other non-structural elements and masonry infills, because those are significant, not significant, even larger than that of the frame, strength and stiffness. So we can't ignore them. On the other hand, the other elements, you said something, pipelines, piping we call. Pipeline, the word pipeline and piping, there is a slight difference. Pipelines we call like the petrol or water or a pipeline which is going from one place to other place. That we use pipeline. Within the building, there are a lot of pipes. Those we call piping. Okay. So within a building, there will be piping for water, sewage. If it is a hospital building, there can be gases like oxygen. There is a piping for suction also. Okay. So all those are also our non-structural components. Okay. So those non-structural components are also governed. The damage to those non-structural components is also governed by interstory drift. Any other non-structural component you can think of? No. Building partition, infill and partition, we can keep them together. Okay. Other than that? Sorry? Chhajja. Okay, chhajjas are not non-structural. Chhajjas are part of structure.
elevators. So elevators.
Elevator. Okay. Behavior of elevator will be governed by, again, interstory drift. Anything else? Piping, elevator, equipment. There is a lot of equipment. Okay. It is not part of our load resisting system, but it is part of our building. And in a hospital building, if the equipment gets damaged, what can happen to an equipment? Even furniture. So let's say this is the furniture. What will happen during earthquake to this furniture? It can damage. That is a very general term. What type of damage? What will be the behavior?
They will be displaced within inside.
So these can move. Okay, slide, topple, what we call rock. So these can rock, topple. So if you think of an X-ray machine in a hospital or a CT scan machine or an MRI machine or the lights fixtures in operation theatre. Okay, all those are also required After earthquake. Even if your building is standing perfectly fine, but all the MRI and even the bottles which you have stored in your pharmacy, if those fall down, all the medicines got mixed up, and there can be even chemical reaction among those. There can be fire. So everything you have to consider when you are talking about seismic performance of the building. So seismic performance, when we are talking performance-based design, then one more difference is that in conventional design, which you studied so far, we were concerned about structural components only. But in performance-based design, we are equally concerned about non-structural components also. Because a building performance, you can't ensure without its content and services. If the services are not functional, water supply is not there, you can't use it. Some of the buildings you can tolerate that. I am not saying that every building you have to ensure that everything should be intact. Okay. But in some buildings at least, that you have to decide, that will be your performance objective. So performance objective for a hospital building is going to be different. Performance objective for a normal residential building is going to be different. In your normal residential building, if there is no water supply for 2 days or a week, perhaps you can manage. But in a hospital, if there is no water supply for a few hours, there will be problem. If there is no electricity in your building, residential building, perhaps you can survive. It's not that big issue. But if there is no electric supply in a hospital, okay, or a control center, so then you can't. So our performance objectives are going to be different for different types of structures. Those are not going to be same for all types of structures. But when we define the performance objective, we have to consider not only the structural components, but non-structural components of the building or structure also. Okay. So when we are talking about hospitals, one type of non-structural components which we are discussing are which are affected by drift, inter-story drift. Because the piping, its behavior will depend on how much relative displacement is occurring between two floors, adjacent floors. That is going to define the damage. But about equipment, suppose a X-ray machine which is kept on the floor, how its behavior will be affected during earthquake? Its behavior will not be affected by inter-story drift. Its behavior will be affected by, yes, floor acceleration. Okay. So how much acceleration is caused on the floor? Now earthquake is causing some acceleration at the ground. The building is moving during earthquake. What do you think? What will happen to the floor acceleration? For this furniture, whatever acceleration of this floor is occurring, that will be like the ground acceleration for this. It doesn't know that what is below. Okay. So whatever is the acceleration occurring at that floor, that will be like an input, a ground acceleration for that component, non-structural component. So what do you think? What will happen to this acceleration from ground to roof? Will it be same? What changes you think in the motion, ground motion, which is input to the structure, and what you are experiencing at the floor? Will it be same? What change will be? Suppose an earthquake, let us say L centro ground motion. We are giving at the ground, at the base of the structure. What do you expect at the floor?
The height of each floor is different, so the line will vary, so that means the acceleration will vary.
Okay, it will vary, but in what sense? What type of variation you are expecting? It will increase along the height? Why you think it will increase?
The story force increases as it goes up.
Yeah.
So, with the mass of the floors as so the acceleration.
Yes, actually it is reverse. The force increases because acceleration is increasing. Force is mass into acceleration. Okay. So acceleration has to increase. That's why the inertia force along the height increases. Okay. But why?
amplitude is same. Above one cycle has to.
Amplitude is not same. Rather, you mean to say that the amplitude is more at the top.
Yes.
So the top of the building is vibrating more. The lower stories are having less
In the same
amplitude
In the same time.
in the same time. So is the time same?
If it is in the
During
same
earthquake, I mean, this is an interesting issue. I don't know whether we discussed it earlier or not. What do you think during earthquake when the building is vibrating? Will it be vibrating with same period? I have given a ground motion here, okay, and it is vibrating. I do not know how. Suppose I take a photograph at an instant of time. How this will look? I take it just a photograph. At any instant I will freeze it. How will it look?
So it depends upon modes of vibration.
Okay. How? It depends on mode of vibration. Every structure we know modes of vibration. Any building like this will have different modes of vibration. The first mode, this is our second mode, this is our third mode. So how does it depend on the mode? Shape is going to be same for building. So let us say this is the shape. What shape you expect here? Will it be this first mode or second mode or third mode?
It's combined shape.
Okay. So if it will be combined, how will it look like? Can you qualitatively draw on your copy? Okay, if you have taken a photograph of this building at an instant of time, how that photograph will look like? What do you expect? So far, you have rightly pointed out that it will be a combination of modes. Fine, we know that it is a combination of modes. It does not vibrate. Many people have this confusion that it will first vibrate in first mode for some time, then it will vibrate for second mode, then it will vibrate for third mode. No, it doesn't do like that. Okay. So it vibrates at any instant of time. It will have contribution from all the modes. All the modes will be contributed. But you have to keep in mind contribution of initial modes is significant, higher modes is insignificant, and it goes on decreasing. Initial first mode, which we also call fundamental mode, has the maximum contribution, 75% to 85% in that shape. Sometimes maybe even 90%. So maximum contribution will come from the first mode. That means the deformed shape will also be governed to a large extent by the first mode. Then over and above that, the second mode will be superimposed. Then third mode. But the amplitude of the third mode will be even smaller. And fourth mode and so on. So this shape will be something like this is our first mode. Then over this, the second mode will be superimposed. Over this, the third mode may be superimposed. And finally what you are going to get? Something like this. But one thing is sure, that first mode is going to govern. Now what, this is about the shape. What will be the period at which it will be vibrating? Or before that, when we say mode of vibration, or we call it natural mode of vibration. What do they mean? What is the natural mode of vibration of the building? When we say that the building is vibrating in natural mode,
Each point will be at the same time period for the same one mode. Like each point will be of same time period, like the same time period in the one mode.
can anybody elaborate more? What does that mean? What you are saying is correct. Can anybody elaborate? What does that mean? When we will say that a building is vibrating or any structure is vibrating in a natural mode. So natural modes are not so natural, first of all. It is not that naturally the structure will vibrate in natural mode. Yeah.
If all the masses move together with the same frequency, it's in phase.
So when same frequency and what did you say?
In phase. Then they are in phase.
Okay. So be clear this in phase, what does that mean? So suppose this top is moving like this, so this will also move like that. So at the same instant of time, these will be at their maximum position. All the masses will attain their maximum position at the same time. Those will attain their zero position at the same time. And here when this will be vibrating in this direction, this will be going in this direction, but the maximum here will occur simultaneously. Okay, so these can vibrate in opposite direction. Vibrating in phase doesn't mean that they have to vibrate in the same direction. That's why we don't use this word in phase. We use that they are vibrating in the same phase, and the peaks are achieved simultaneously, and zero position is also achieved simultaneously. Okay, here it will be vibrating like that. So this is a special condition where all the masses are vibrating together. Suppose there is a building, I want to make it vibrate in first mode. How can I make it vibrate in first mode? Suppose there is a building, I deform it at the top and leave it. In which mode it is going to vibrate? First mode? No. There is a lab just other side of the you might not have gone there, but let's open that and see how you can make. There are some models and vibrate interval. Okay, so you can just try there how you can make it vibrate. If you deform it and leave it, it is not going to vibrate in the first mode. It will again vibrate in a combination. If you want to make it vibrate in the first mode, you have to deform it in the motion. If you deform it like this, then only it will vibrate in the first mode. Otherwise, how you are going to vibrate in second mode? That's the first mode. I can give a displacement at the top and leave it. That may give you an illusion that it will vibrate in the first mode. How to make it vibrate in the second mode? I have to deform it in the second mode, then it will vibrate in the second. Okay, so that's why I said that these natural modes are not so natural. You have to put a lot of effort to make your structure vibrate. The other method of vibrating it, that you apply a simple harmonic motion at the base with frequency of the first mode. You give an excitation, a harmonic excitation with first mode frequency. Then it will vibrate in first mode. Resonance will occur with the first mode and it will vibrate in the first mode. Similarly, if you give the base motion with the frequency of the second mode, it will vibrate in the second mode. So these are the natural ones. Okay. So now, can you tell me, are the masses, different masses in a building during earthquake, those are vibrating with the same period? No, because it depends upon the combination. Okay. So they may not vibrate, but predominant mode is first mode. So predominantly those will be vibrating the same time. Slight differences there because of the higher modes, but mostly it will be vibrating with the first mode. So that's why the top in the same time is going to cover larger distance. The amplitude is more. So the top story, the top floor has to cover more distance in the same time. The lower story has to cover less distance. And that's why if the displacement at the top is more, its velocity has to be more, its acceleration also, because of the single harmonic motion. Okay? So the acceleration at the top is going to be more because of the predominant fundamental. Suppose first mode was not predominant, second mode was predominant. Let us say, hypothetically we assume, although it will be the first mode always. But suppose it is the second mode, then also you are expecting the same thing, no? In that case, top and a story below, those will be vibrating. So in that case, where do you expect maximum acceleration? Here and here. So it will depend upon which mode is predominant in the structure. Mostly, I mean, in all natural cases, it will be first mode mostly, which will be bilateral, which will be predominant. So that's why we get a variation of acceleration also of the height, which is governed by first mode. But first mode alone does not govern, other modes are also. But one thing is sure, that at the top it is going to be more than at the bottom. So the acceleration increases. Any other change in the ground motion you are expecting? What happens when the ground motion is transmitting through the soil column? We discussed this, the effect of soil. I mean, not we discussed, I did not teach, but it must have been discussed in the first class. So what happens in case of, you might have been told a case study of Mexico City. What happened in Mexico City? Anybody? Huh? Sorry? Waves get amplified. Okay.
At a larger distance from a person.
Okay. What else?
So in between there was no amplification, there was less amplification, but at the side there was more amplification.
So those got amplified. Something similar is happening in our building. Building also, you can think like a soil column. Okay, a soil column. Only thing is that its extent is very large, but because it is uniform, you can just cut a small column. Behavior of that small column will be same as all soil layers. You can think that building is also having the same, and these floors are like the different layers. As the layers have different stiffness because of the different value of G, because of the different shear wave velocity Vs, that is square root G by rho. Okay, so in the same way, our stories, which you can think as layers, those are also having different stiffness. So you can consider the behavior of the building very similar to that of soil column. So what happens here? One thing is that the ground surface is having higher acceleration. Okay. There is another very important change in the ground motion characteristics. What is that? Amplification is one effect of the soil. What is the other effect? Filtering. What does it do? If you plot the response spectrum, you have seen the response spectrum of Mexico City. So in Mexico City there was damage, lot of damage, which was not expected at such a long distance from the epicenter. More than 350 kilometers from the epicenter, you don't expect the damage. So damage occurred, that was the one observation. Second observation was that that damage was selective. It occurs only between 5 to 20 stories. Why? It occurred in 5 to 20 stories. Because of the filtering action of the ground motion. When the ground motion got or it transmitted through the soil, the frequency, the fundamental frequency of that soil column, okay, all the energy got focused around that frequency. So if you see the shape of the response spectrum, we get a peak of that around 2 seconds. Okay. So you just look at that. So we get a very high peak in the response spectrum. PGA increased, but increase in PGA was not that much. Increase in spectral acceleration was much higher. So this is called filtering action. Same thing is going to happen here also. Okay. So what will happen? When the ground motion is passing on each floor, it will get amplified, and at the same time there will be filtering action. So those non-structural components, those equipment here which have their frequency close to the fundamental frequency of the structure. So if this is also having period close to T1, what will happen? It will be resonance-like situation, quasi-resonance will be. Okay? Because the ground motion which came here at the ground, that was having a frequency band. Lot of frequencies were there. What the building will do? Out of those frequencies, it will filter out. and all the energy will be transmitted corresponding to the fundamental, the harmonic corresponding to the fundamental period of the structure. Lot of energy will be focused there. So those secondary elements which have the period close to the fundamental period of the building, those will be subjected to very large damage. Same way as the 5 to 20-story buildings, their period match with the period of the ground motion. Okay? And by chance, if the period of the soil here, that is also close to T1, what will happen? That is the extreme condition. So building period is also matching with the soil period. So one filtering action will take place here. Building will go into resonance. Another filtering action. Okay. This situation we call double resonance. So the frequency of the secondary component matches with the frequency of the structure, which again matches with the frequency of the soil. Okay. So you have to be very careful about those secondary elements which are having their frequency close to the fundamental frequency of the structure, or fundamental frequency of the structure. Okay. So floor acceleration is also important, and when we are talking about floor acceleration, we have to consider the frequency or frequency ratio. So secondary structure, let us say period is T star, and building period T. So if this T star by T1 is close to 1, okay, then the secondary elements will be subject to much larger force. Okay. So floor acceleration is also one of the EDP. This is also a parameter which we have to check. If I want to control the performance of my building, I have to control the floor acceleration also, because some components, so these non-structural components, we classify into 3 categories. As drift sensitive, drift sensitive components are those which are connected between adjacent floors, like piping, partitions, infill, or any other equipment which is connected between 2 floors. Okay. Then we have acceleration. Sensitive components, non-structural components. Their behavior is governed by floor acceleration. Those are generally connected to 1 floor. And whatever is the acceleration at the 1 floor, either they are simply capped over the floor or they may be anchored to the floor. So if we have to avoid toppling and sliding of any equipment, we have to anchor it. And how much force will develop in those anchors, that will depend upon the floor acceleration. So due to floor acceleration, 2 things can happen. One thing is, if the equipment is not properly anchored, it will topple, fall down and get damaged. Okay. If there is a light hanging from the roof, that light may fall down, the fan may fall down if it is not properly anchored. Okay. Or if it is properly anchored, the acceleration may be so high that the internal damage may occur in that area. Because any equipment can also sustain some level of shaking. If the shaking is more, if you put that equipment on the shake table and shake it for the floor loading, it may happen that the equipment may also not be workable. It may not be in the working condition, operational after that. So these 2 types of damage can happen. Then there are some non-structural equipment which are sensitive to both drift and acceleration. These elements are sensitive to both drift as well as acceleration. Now, if you have to improve the performance of your non-structural element, what you are going to do? Structural performance, let's first say, you want to improve the structural performance of your structure. How you can improve? Structural performance is covered by inelastic deformation. Okay? So if you have to improve the structural performance, what we are going to do? How? How you can control deformation in a structure? You know, but how you are going to do that?
Well, according to design reinforcement.
So how you will design the reinforcement to control the deformation?
Like we have deflection limits, we can specify deflection limits.
Deformation can be controlled by stiffness. Deformation cannot be controlled by strength. The deformation can be controlled by stiffness. So if you increase the stiffness, now if I am increasing the stiffness, is the performance of the structure going to be good or better or worse?
Sometimes worse. Sometimes worse.
Sometimes worse and sometimes good also. So in which case it will become better and in which case it will become worse if you increase the stiffness of the structure.
In case of earthquake, we don't want the structure to be
Strength. Why?
if we stretch it straight, then as soon as there's a acceleration or there's a vibration, the structure won't be able to bend accordingly. The structure may develop cracks.
So whatever you have studied so far, that a flexible structure is better for us. More flexible it is, more period, longer period it will have, and as the period is increasing, you have seen the shape of the response spectrum, the force is going to decrease. That's what you have learned so far. Okay? But it is not correct understanding. It is true if your structure is elastic. Okay? This understanding is okay if your structure remains elastic. So if you are comparing two elastic structures, then the structure which has been designed for longer period will sustain less forces. But we never design our structures. So this is one myth, one misconception that flexible structures work better. Okay? If you have to control interstory drift, you have to increase its stiffness. Okay? But you remember, we did not talk about the displacement, absolute displacement. We talked about post-yield displacement. So how to reduce post-yield displacement? How you can reduce post-yield displacement? We discussed the behavior. If it is hypothetical elastic structure, then the force versus displacement relationship is linear. This is the displacement of elastic structure. In elastic structure, initially it will follow the same path. Then this is our Fy. This is delta y. This delta inelastic is same as delta u. Okay, and this is our plastic displacement or inelastic displacement. We have to reduce this because this is causing damage. Till this point, there is no damage. The damage starts from here and it goes on increasing and here it collapses. So equal displacement principle, you know that delta u is delta E. the response of or the maximum displacement of the elastic and inelastic structure is same. If you are designing your structure not to yield, then whatever maximum displacement you will get. If you design your structure, which usually we do to yield during earthquake, then also its maximum displacement will be same. Okay, and this is the damage. How you can reduce this?
Increase the strength of material.
Increase the
Strength of material.
not material. Material strength it may not be possible because steel, if you have already used Fe 500, how you can increase? So the strength of material you cannot increase, but the strength of the structure you can increase. How? By putting more material. So increase the size of the members. So the strength of the structure you can increase. So suppose you change Fy to Fy dash. The damage may be reduced. So here also, how you are going to improve the performance of the structure? By increasing the design force. So method is same. In performance-based design, we are not doing something else. We will be doing what you have learned. Okay, but this Fy dash will be decided based on how much damage you want to accept. Let us say for a structure, this is the building. Okay, you apply this force. Total force will present as a ratio, which is summation of all these Qi. And you plot ratio versus this displacement at root. Our graph will be something like this. Okay, I will represent it by equivalent bilinears. We'll talk about this in more detail. So this becomes my delta y. Okay, this is delta. Delta u is representing collapse. Delta y is representing no damage. So here there is no damage. Here there is full damage. In between, you can decide how much damage you want to accept. So these are your performance levels. Which performance level you want. That we will decide based on how much damage you can accept. And that damage will depend on how much out of the total capacity of plastic deformation you are utilizing. You are using. The total plastic deformation capacity which your structure has is delta P. If you utilize full, the structure will be at the verge of collapse. If you utilize half of that, the damage will be less. Still it has margin to collapse. Performance will be better. If it is very close to yield, that means the damage is minimal. You can't even see it from your eye. Okay, so like that, you can decide. So you can decide how much you want to permit. Let us say I decide I want to permit only this much. So then, I have to decide this level Fy dash in such a way that this is equal to the displacement in elastic displacement I have decided. Yeah.
Is it like to increase the performance in inelastic and increase size of the numbers? So my question is like in case of inelastic deformation, we consider the inelastic deformation after the formation of the plastic range. So the range that we are getting in the graph, in the stress versus strain graph, that range is the range that is defined by after the formation of plastic range. The amount of
Right. Plastic hinges are forming here.
So the amount of movement that is taken by the material after the formation of plastic range.
Sorry, moment is taken by.
I mean,
There is no additional moment taken.
I mean, the the weight bears.
Curvature, slope, and deformation cannot.
That,
But moment cannot increase.
so even if we increase the size of the members, if we increase the size of the members, the elastic range will anyway increase. The strength it takes will increase. But once the plastic hinge forms, won't the range still be similar to the
Range will be similar, but what I will be utilizing out of that will be less. So here you see, suppose this is my structure capacity. Okay, so in first case it is utilized fully here. In second case, this is the capacity, but I am utilizing only this much. So capacity, the plastic deformation capacity will remain more or less same. When you change the size, there will be some small difference in the plastic capacity also. Okay, but we can assume that that is negligible. Let us say the plastic deformation capacity remains same. But when you increase the strength, the yield strength, out of that same capacity, what you are utilizing, that will reduce. Okay, and when you are reducing how much deformation you are permitting out of the total, you are reducing the damage. So if you are reducing the utilization of that plastic deformation capacity, you are reducing the damage, or in other words, you are improving the performance. Okay, so finally, now you can understand the full overview of the method. We are controlling the plastic deformation in our structure. To control the plastic deformation, if I want to reduce the plastic deformation in my member, what I have to do? I have to increase its strength. So ultimate outcome is similar, what you have done there. There also, if you design, I mean in your first semester also you learned that if you design for target force, better the structure is. So ultimate answer is same, but here you can estimate how much increase in the capacity, strength. What strength I should design for the targeted performance level here. So the performance level I will target here, and corresponding to this targeted performance level, how much should be this value of Fy dash? Okay. So as far as the structural components are there, the design procedure remains same. You have to estimate or you have to increase the strength. Only difference is that previously you were not knowing how much increase is enough. Now you will be able to estimate that to achieve this particular performance level, this much increase. So that's why we call it performance level. Strength, we are deciding with respect to the performance. We can relate the strength required with the performance objective we are targeting. That's the difference between the two methods. Behavior of the structure will remain same. We are not changing the structure. Structure will remain same, which remains elastic up till a certain load, then it becomes inelastic. It goes on deforming, but the force does not increase. Then it reaches maximum displacement and it comes. That behavior is going to remain same. We can't change it. Okay? But understanding this behavior, we can calculate that for my targeted performance, what is strength is required. That's what we are going to learn. This is about the structural component, but as I told you that non-structural components also are important. We can't ignore non-structural components. So if I want to improve the performance of non-structural component, what should I do? I told you 3 types of non-structural components. Acceleration sensitive, drift sensitive, acceleration and drift sensitive. So if I have to improve the performance of drift sensitive components, what I have to do? Yeah, how? How you can decrease the drift?
Stronger.
Not stronger, stiffer. Always now, I mean this is a common mistake. We confuse always between stiffness and strength. Stiffness and strength have 2 different properties. Okay. Although if you have to increase stiffness, then also you have to increase the material size of the member. If you have to increase the strength, then also you have to increase the material. Okay, but these are 2 different properties. These are not same. So we have to provide stiffer structural elements. Means You can provide a shear wall. Either you can increase the size of the columns and beams, or you can provide shear walls. So the stiffness is going to increase, the drift is going to reduce. Okay. But when you are reducing the drift by increasing the stiffness, what will happen to the acceleration? Floor acceleration. Will it remain same? Will it decrease or will it increase?
Increase.
Why?
Increase.
So why you are shy of saying that? So time period is going to reduce. If you are increasing stiffness, the time period is reducing. What will happen to the floor acceleration? You know the shape of the response spectrum. So SAT1 is going to increase. Okay, and it will be further amplified by the building. So that is going to increase. So if you are increasing the stiffness, the drift sensitive equipment, drift sensitive components, performance will improve, but acceleration sensitive components will reduce. In a hospital, you have both. So what is the solution?
We have to mix balance.
How? I mean, there are two contradictory requirements. In that case, base isolation or damper is the solution. So if you have to control, or suppose you are not able to make balance, you can't come out with an optimum stiffness which controls drift as well as acceleration. Both are within limits. Suppose, and it may be possible because you have contradictory requirements. Some of the equipment, the performance is governed by drift. Another set of components, the performance is given by acceleration. If you reduce drift, acceleration increases. Okay, so what you have to do? You have to use some technique by which both acceleration and drift are reduced. So base isolation, that's why it is recommended that in case of hospitals, base isolation should be used. In some cases, base isolation can also be problematic. I will talk about that in more detail. But in general, if it is a hospital building, the most ideal solution is base isolation. So hospital buildings, we promote base isolation. Some of you are doing a course on response control in this semester. There you will learn in more detail. Now there is an IS code also, IS 875 part 6 most probably, part 8 6. So that is on base isolation, you can learn. You can also take this base isolation as your dissertation topic. Okay. And dampers. Dampers also control both drift as well as acceleration. Okay. How? We can also talk a little bit in this course, but you will learn this in quite detail in your response control course. Okay, so that's an overview of performance health. When we meet on Monday, we will continue.